Good morning and a warm welcome to another virtual session of the U3A here in Hermanus. As you may know, there's quite a collection of geologists that have retired to Hermanus, and with their cooperation that have given us wonderful talks about the geology of the Cape and the areas around us. And I'm particularly happy to welcome Dr. Hayley Cawthra this morning. She is a senior scientist in the Geophysics and Remote Sensing Unit of the Council for Geoscience, and a research associate at the Nelson Mandela University in the African Center for Coastal Palaeoscience. She holds a PhD in geology from the University of Cape Town and has research interests in marine geophysics, Quaternary sea level change, the human use of ancient coastlines, and the emergence of paleo environments. As she will explain to us, she spent more than 10 years researching the coastline of the Cape, much of which is submerged by the sea right now. Hayley, thank you very much for your presentation, and we're really looking forward to you guiding us through the complicated and fascinating world of our coastal areas.
Hi, good morning. Thank you so much, Gert, for the introduction, and thanks everyone for logging in to listen to this presentation. I'm from the Council for Geoscience and the Nelson Mandela University, and I've spent the last 10 years or so working on mostly on the theme of submerged landscapes and mostly on the Cape South Coast seafloor, so approximately from Cape Agulhas to Plettenberg Bay, with most of my focus near MOSSEL Bay, but certainly not taking away from the areas to the east and the west of that. I'm always excited to take people on a journey underwater, so I hope to do that this morning. I'm going to come back to this map at the end of the presentation, which has taken me, like I said earlier, the better part of 10 years to put together. It might not make much sense as it is right now, but hopefully in 45 minutes time you'll have a lot more context, see sort of the impact of the work that we've been able to do. So firstly, a bit of context on marine geology in general and why we map the seafloor, how we map the seafloor. I'm going to start off by showing this map here, which was revealed to the world in 1978. So the map shown here was the first map produced of the seafloor, and it was put together in the years following World War II. It took the better part of about 25 years to compile from all sorts of military-related data. And the map was made by a lady called Marie Tharp. She actually recently, in July, there was quite a lot of publicity online about her because it would have been her 100th birthday. And in marine sciences, she's highly celebrated at the moment, acknowledging this wonderful work that she did. So the map that was put together by her and published in 1978 basically remains the benchmark of what we understand about the topography of our very own seafloor. Strikingly, not much about this map has changed since it was put together in 1978. The broad structures on the topography of the seafloor, as they are here, are basically as we still understand them now. There have been certainly bits that have been tweaked in areas that have been mapped with high resolution, but for the most part, we haven't learned that much more about our ocean floor in the last 40 years or so. We live on the blue planet, and the ocean covers about 71% of the surface of the Earth. The oceans are, of course, fundamental to sustaining life, controlling climate, enabling commerce. They have all sorts of benefits. What's quite incredible to me, though, is that many of the planets remain better mapped than our very own seafloor. There's a book that was being put together several years ago called Soundings, and it's all about the story of Marie Tharp, and it's a really good read. I strongly recommend it if anybody is interested. So like I've just mentioned before, how we map the seafloor, those techniques are basically, they've been highly refined in the last 10 years, but the general principles behind them are basically unchanged. So we're able now to use sophisticated satellite technology, to use remote sensing techniques and look up into space and map the planets and get a really good idea of their structures and their makeup. But we can't do that on the seafloor yet. And the reason for that is electromagnetic waves, those used to map in space, become highly attenuated through seawater. So those systems that we use to look up, they can't be flipped over to look down. And as a result, we still have to mount sensors on a vessel and steam up and down, getting continuous coverage on a patch of seafloor in order to map it. In our team, we refer to that as mowing the lawn, because that's what we think we're doing, to ensure 100% coverage of whatever block we're working in. At the Council for Geoscience, we have 5 different instruments that we generally use to map the seafloor, and the one example shown here is multi-beam bathymetry. The Quaternary period is the time period that most of this presentation is going to deal with today, and that refers to the last 2.5, or actually 2.6 million years of geological time. Within the Quaternary period, there's the Pleistocene and the Holocene epochs. We're currently in the Holocene, although some people argue that we're in the Anthropocene, which probably started after the Industrial Revolution or sometime around then. But because we're in it, we're still unable to really define it, so technically we're still in the Holocene epoch. You'll see on this map, I've got areas that are shown in red, and those are continental shelves that become exposed when sea levels drop. And sea level is certainly not static. The elevation where sea level sits right now, which is obviously 0 meters relative to mean sea level because that's where we are, this benchmark changes constantly. And it changes in response to ice ages and interglacial cycles between those ice ages, which are periods of warming like right now. So sea level constantly fluctuates, you've got to bear that in mind. And the Quaternary period is the one of relevance to us right now, the last 2.6 million years. And in fact, most of this presentation will deal with the last few 100,000 years, which is actually very short in terms of geological time. In South Africa, because of the projection of this map, the Mercator projection, our continental shelf around the Cape South Coast doesn't look as impressive here as some areas globally, like around the tropics, for instance. But that's actually just a function of the projection. And in fact, there's 100 kilometers or more in certain places from the coast to that baseline shown at the edge of the red. Showing graphically what this means with these changing sea levels. This is a sea level curve shown at the top here. And the red line is present mean sea level, so where the coast sits right now. The blue box shows the minimum points about 130 meters below present, and the maximum points up to about 11 meters above present. So sea level constantly fluctuates between these two benchmarks of about 11 meters above and 130 meters below. Right now we're sitting over here. What's quite obvious is that for about 90% of the Quaternary period, the continental shelf has been exposed and sea level was lower than what it is now. The way that these sea level curves are expressed is in marine isotope stages, which is the MIS notation. And these marine isotope stages have been developed from foraminifera, or microfossils, that are very sensitive to changes in sea surface temperature or any oceanographic conditions, and they die out quite readily. So their stratigraphy has been very well defined in terms of biostratigraphy, and these periods have been named accordingly. So the marine isotope stages with negative numbers are the warm periods. Currently we're in marine isotope stage 1. The last big one was 5, specifically 5E. And marine isotope stage 11 is another one I'm going to come back to just now. The implication of these moving sea levels from a geological perspective is that sedimentary systems that are now on the coast move with the changing sea level. So you expect beaches, dunes, rivers, wetlands, all the features of a coastal plain that you see now, we expect those to shift out onto the continental shelf during times of lower sea levels. And sometimes when we're lucky, those get preserved as rocks or as deposits on the continental shelf. So to give a little bit of context on the geological setting of the Cape South Coast, this is a geological map of the area, which a lot of you will probably already be familiar with. We've got the approximately 3,000 meter Cape Fold Belt shown in blues and greens that separates the coastal plain in yellow from the interior or the Karoo on top of the plateau. What people are not always familiar with is what happens offshore. And for the most part, the deposits on the continental shelf are quite different to what they are along the modern day coastal plain. So shown in oranges and yellows here are sediments that were laid down since the breakup of the supercontinent Gondwana. So when Gondwana broke up, the Indian and Atlantic Oceans opened for the first time. This was about 130 or 140 million years ago. When that happened, a lot of sediments that were shed off the top of the Cape Fold Belt and from the hinterland areas and deposited onto this newly formed ocean floor into sedimentary basins. These Mesozoic strata are usually the orange ones on the map, which are made up of clay stones and siltstones, some sandstones, and generally the yellows are things like limestones that we lay down later. There are only a few bits of the Cape where the hard rock geology of the Cape Fold Belt extends offshore. One of them is near Walker Bay. From Walker Bay, here's Walker Bay over here. From Walker Bay down towards Cape Agulhas. Also from Cape Hunklip and False Bay. So basically from Hunklip all the way down towards the southeast. Another place where this happens is in the Tsitsikamma area and off Cape St. Francis. But for the most part, what we find on the seafloor is a little bit different to what we find on the modern coastal plain. That's important to keep in mind. Also, the erodible nature of these deposits has led to the wide, flat Agulhas bank. So that's a lithological phenomenon. So the soft rocks, highly erodible. Sea levels have always changed, and they've kind of flattened out a lot of the stratigraphy out there, making that Agulhas bank. One exception is the Alfred Banks, shown in green over here, which is an ancient volcano that was the last puff of energy as Gondwana pulled apart. So zooming into the main focus of this talk, I'm going to get into a discussion about the area extending from Cape Agulhas in the west to Plettenberg Bay in the east, and looking at the foreland area, the coastal plain, and out to the edge of the continental shelf. So most of our work in the last 10 years is focused on this zone specifically over here. So just another line of context on why the South African offshore environment is so important is that, especially on the Cape South Coast, so South Africa is bordered by these geostrophic currents. There's the Agulhas current that comes down from the Mozambique Channel and from Madagascar. It brings really warm waters to the south. The Agulhas current flows at a consistent speed of about 4 meters per second for the most part, and it's extremely warm compared to the cold Benguela, which is less well defined, and it flows up the west coast. Where they meet on the Cape South Coast, there's a lot of sort of eddy formation and shearing off both currents, and a lot of mixing that takes place. And as a result, it's led to really high biodiversity, both in terms of marine species like shellfish that live along those coasts, and also having a knock-on effect on the local vegetation, which is the Cape floristic region. So those are both extremely high diverse ecosystems, and they all tend to converge here on the Cape South Coast. So it's a really interesting place to study what happened in the past. Lots of little nuances and fluctuations. And if you think of that wide continental shelf, it means that during times of low sea level, the coast is actually much closer to the core of this warm current. So in the geological record, we're very fortunate to have great preservation of Quaternary deposits along the Cape South Coast and in South Africa in general. Shown at the top is a topographic map, and all the yellow bits are these Cenozoic rocks. A lot of these are Quaternary sediments. And these are left normally remnants of this high stand periods, so marine isotope stage 5, marine isotope stage 11 in some places, if we're lucky. And these are great analogues for what we expect might happen in the future. So you have to understand the past in order to project forward into the future. And when we're looking for sea level indicators in the geological record, we're often looking for a special contact between shore face deposits and foreshore deposits. So essentially it's where the beach meets the area under the waves. It's accurate to about 1 or 2 meters in the vertical, which for our purposes is just fine. And we've got a lot of evidence for the last high sea level, which was about 6 to 8 meters above present, especially next to river mouths along the Cape South Coast. But we also, in some places, have evidence for marine isotope stage 11, which was about 13 meters above present sea level. But when you model the effects of isostasy, it comes down to about 11 meters above sea level, although the actual height right now is 13 meters above present sea level of those deposits. They're probably laid down about 11 meters above. And that marine isotope stage 11, for many reasons, seems to be the most appropriate analog of what we could expect in the current interglacial. So maybe in the next few thousand years, local sea levels might reach a height of about 11 meters above present sea level. Super important for forward planning and for understanding that sort of system. When we're studying past sea level change from a geological point of view, we're always looking for the place where mean sea level probably was. And in a rock record, you're looking for foreshore deposits that were laid down on beaches and shore face deposits that were laid down underneath breaking waves. And if you can find that contact, it's a basic approximation of where sea level probably was at the time. Another interesting thing about the Quaternary period is, of course, human evolution. It's the origin of our species and how we came to be where we are now. And this is probably the most profound reason that people are interested in the Quaternary period, is the human link, the human aspect. So very briefly, fossil and genetic evidence shows that our species of Homo sapiens originated somewhere in sub-Saharan Africa, somewhere approximately within the last 200 or so thousand years. Refinements of the L haplogroup, which is the oldest genetic lineage within Homo sapiens, demonstrates that our progenitor population may in fact have come from the southern bit of sub-Saharan Africa and maybe even South Africa. By about 50,000 years ago, Homo sapiens moved up and out of Africa through the Levantine corridor in the Arabian Peninsula and spread all over the globe. What's pretty fascinating, a lot of recent work on genetics has shown that there's a lot of genetic admixture between various species. So there was modern humans, which were our early ancestors, Neanderthals, Denisovans, and one fourth unknown lineage yet to be discovered in fossil records. And in fact, there was intermixing between most of these populations. But what remains pretty clear is that everyone else went extinct, and the only anatomically modern humans that remain are Homo sapiens. Anthropologists will often believe that this has got to do with our burgeoning cognition and our ability to collaborate and cooperate in working groups and survive across a broad range of diverse environments. I'm going to focus most of this talk on Pinnacle Point specifically, but the map on the left shows that the Cape South coast has some of the richest Middle Stone Age archaeological sites and records anywhere on Earth. Encoulders is a really important site, which is in Walker Bay, Lombos Cave, Pinnacle Point, Nelson Bay Cave, Classies River. These are just a few shown for reference. They're all near-coastal sites, which means that they're on the coast at the moment, but they weren't necessarily always because of those shifting sea levels. Often, the best caves that are preserved, such as here at Pinnacle Point, are the ones that sit higher than about 6 meters above present sea level. And this is because of those interglacial periods where Earth was warm and sea levels were high. So if you consider that for 125,000 years ago, archaeological remnants in caves would have probably been washed out had they been closer to modern sea level. So Pinnacle Point and other archaeological sites along the Cape South coast all demonstrate that people most certainly relied on coastal resources. So this means that in the archaeological sites that are preserved along the coast now, there's a lot of evidence for shellfishing and use of coastal resources. And there's often an abandonment of the sites during times when sea level was low. So people were living on what is now the submerged continental shelf, as this was an exposed landscape. Shown up here on the top right, the neo-coastal plain, this is the modern coastal plain. The present coast extends approximately along here where my mouse is pulling, and this whole continental shelf would have been exposed during the glacial maxima. Off MOSSEL Bay, that's a distance of 100 kilometers offshore. The people generally foraged within 5 to 10 kilometers of the coastline. So understanding that the offshore environment was important, I started working with archaeologists about 10 years ago, specifically Curtis Marion and his team. And it's been a really interesting scientific journey for me, and for all of us, in fact. So we got together and we were discussing that the coastal plain and the shelf are continuous. We needed to understand the continental shelf evolution using marine geology in order to understand the real impact on people living in this environment. So seeing the continental shelf as a submerged terrestrial landscape with soils, plants, people, and everything that you find along any coast, we decided to go out and map this shelf to try to reconstruct this submerged environment. The first time that this idea was published was actually in 1972 by Professor Dingle and Dr. John Rogers. They wrote a fantastic paper in 1972 based on John Rogers' master's work, actually. And they wrote there that they acknowledged that this broad Agulhas bank on the Cape South Coast shelf was going to be really important for looking at paleogeography. And they wrote here, even then, that disciplines needed to come together, including archaeology, botany, meteorology, zoology, etc. Unfortunately, back then, the technologies weren't really conducive to being able to do that kind of integrated work. But keeping that in mind and building towards this over the last 50 years, finally, we've been able to do something about it. So just in May last month, or sorry, 2 months ago now, gosh, our team that have been working together for 10 years, we published a special issue in the journal Quaternary Science Reviews that describes this PALAEO-AGULHAS plain, as we call it, the lost world and extinct ecosystem. We drew our inspiration from a lot of multidisciplinary work that's been done on fynbos and on the Serengeti, which was published as a sort of describing the Serengeti as an entire ecosystem. And we saw the submerged landscape as an entire ecosystem. And I'm not really going to go into other people's work on this, but we've done a lot of modeling on climate, vegetation, soils, animal movements, all sorts of things. I'll touch on some of these things within the presentation that I specifically worked on, but it's been quite a great project to be involved in. So to map out the continental shelf, as I mentioned earlier, it's not that easy because you've got to literally paint the seafloor like as though you're mowing a lawn. And my colleagues and I spent 3 months in Mossel Bay back in 2011, collecting multi-beam bathymetry, side scan sonar, which gives you a textural image but with no depth values, 2 different types of seismic that give you almost a slice of cake through the seafloor, like a 3D perspective. And we also collected some magnetic data. In order to sample the Quaternary rocks that I wanted to have dated to figure out changes in sea level, we did about 50 scuba dives, but the conditions there are not great. And it wasn't too easy to get this done. I mean, the visibility is often close to 0, and you've got to hammer off a piece of rock that weighs about 50 kilograms to send it to the surface in a lift bag. These are pictures. This is the hammer that we use chisels and crowbars and all sorts of weird tools. That's a photograph of one of my colleagues to show you that sometimes we can see almost nothing. We use lights and strobes and torches to light up the bits of the outcrops. And we would hammer off a chunk of rock, for instance, like that, send it up to the surface in a lift bag, and the unfortunate person on the boat has to pull it in. We all do these different tasks. We all sometimes dive and work on the boat and skip around. Mossel Bay is unfortunately not too famous for tropical diving conditions, but it is well known for its great white shark population. So we had to take special precautions and use cages for our safety stops and any decompression stops as well. I've got a little video here I wanted to show you. This is a video that we took swimming down the shoreline on our way to the seafloor. We had a torch on just to, we always dive with lights if it's low visibility. And I just wanted to show you what it sort of feels like to go diving in a place like that. There's a lot of muddy particulate matter in the water, so it's not too, the visibility is not too good most of the time. But when we get to the bottom, as soon as you touch the bottom, we get straight to work. So here we were just identifying which ledge to hammer, and we would have immediately started with our things that we've got to do. Later on, we also had the opportunity through a bilateral German-South African project to get use of the vessel Meteor, which is a beautiful research vessel that works all over the world. It's a German vessel, and with this, we were able to take 6 cores off Mossel Bay. I chose areas that were in ancient river systems and ancient lagoons to try and get an idea of the terrestrial landscape at the time. So just to show you here, the dark blue bits, Mossel Bay and Vlees Bay, is where we collected full coverage geophysics for 3 months. The black lines are seismic profiles that we went all the way from Cape Infanta to almost to Plet. And then there were 6 cores taken on the shelf shown by these stars. So all of our dives were done in this area in Mossel Bay. So with all of this, we're able to start putting things together to eventually make the map. To show you what the seafloor of this area looks like, off the Great Brak or the Grootbrak River, there are beautiful Pleistocene or Quaternary deposits. These are ancient coastlines. They are cemented beaches and cemented dunes, called aeolianite, which are cemented dunes, and sometimes beach rock, which are cemented beaches. The Great Black River carved through them after they were cemented as rocks, which means that they're relatively old. For the most part, the bay is quite sandy and quite low relief. This area is underlain by Cretaceous-aged siltstones and claystones that were laid down when the Indian Ocean opened, which is a very erodible substrate, and it's why the Agulhas Bank is so flat in general. Offshore of Pinnacle Point, you do have coastal caves extending out onto the seafloor as well, but only for about 3 kilometers. If you looked at the gradient, this profile here comes from offshore of Pinnacle Point. You can see the shadow and the bathymetry, so there's a steep drop off and then the flattening out of the Agulhas Bank. The coastal caves were pretty cool offshore of Pinnacle Point. So this is Cape St. Blaise, shown on the bottom right. Pinnacle Point is just off to the left. And we can never map within the wave area because firstly, the water is too aerated for the geophysical instruments to be able to see anything, but also because it's just dangerous to go there with a small boat. So for 3 kilometers out, these rocks extend offshore. You have little embayments, exactly like the embayments along the present coast. And showing you the bathymetry at the top. If you put sea level at a depth of 23 meters, where you're at the base of the coastal caves, it would have been analogous to our present day coastline. And we did in fact dive in these areas looking for any archaeological sites, but we didn't expect to find any because of our high energy coast, and we unfortunately didn't. But I'm sure that people would have occupied those caves during times of low sea level. So offshore of the Great Black River, those rocks that I showed you earlier give an indication of what paleo winds were doing at the time, because they're dune rocks that were laid down in aeolian systems. And it looks as though southwesterlies and easterlies have always dominated the Cape South coast. For example, this is from 90,000 years ago, and we know that because of our diving and sampling, and we had the rocks dated. There are also paleo beaches on the continental shelf. Shown here as these low relief ridges, I've called them. But what's pretty interesting about this very wide, very low relief shelf is that everything is expanded and extended and everything's kind of far apart. So in the modern coastal plain, everything's quite compressed. And if you consider somewhere like Wilderness, where dune ridges stack upwards, when you drop sea level, the situation is completely different. There's a lot of accommodation space, which also means that the rivers behave differently. And this is a multi-beam image of the Great Black River. The channel was up to 800 meters wide at times, which is completely crazy to try to imagine compared to what it looks like now. It's quite a small, sort of steep, narrow river at the moment. But the rivers on the Cape South coast behave completely differently once they reach the continental shelf. I'll show you later as well, the Gerrits River had a floodplain of 18 kilometers across, which is pretty astounding to try and imagine. So to show you some of the rocks and how they relate to sea level change, this is back to the same sea level curve that I showed you earlier. During the periods of low stand, when sea level was falling towards glacial maxima or ice ages, beaches and dunes, wetlands and rivers, all of these elements of the geological environment are left behind in the sedimentary record and cemented into rocks that we've been studying. So dunes, like I said earlier, everything is very widely distributed on this really broad continental shelf. And the dark orange bits here are areas of aeolian deposition or dune rock, extremely wide dune systems, but they don't ever get too high, they never reach high elevations. So for instance, the maximum elevation of these dune systems that we mapped was about 8 meters, which isn't very impressive compared to places like Wilderness or Alexandria. What's also really interesting, something that we found offshore of the Great Black River, was evidence of a meltwater pulse, which is a time when sea level rises extremely quickly, related probably to a large chunk of ice sheet breaking off. And in this case, it happened 140,000 years ago. Sea level was rising up the profile, and at about 140,000 years ago, there's a time where these 3 ridges that my mouse is going over now were all laid down within about 1,000 years of each other, across a distance of about 3 kilometers. And they were laid down at a time when sea level was rising at about 4 to 5 meters per century, which is about 4 or 5 times faster than at present. So when we're looking into the future, we have to also bear these sorts of things in mind. The post-glacial marine transgression refers to the period from the last glacial maximum to now. It's the last 20,000 years of time. And basically, sea level rose really quickly. It took 20,000 years to rise 130 meters. So it was 130 meters lower during the glacial period, and it's reached where it is now in just 20,000 years. That's the case all over the world. What this did on the Cape South coast was it submerged lagoons that were already there. So this would have been an old stranded lagoon that was exposed when the sea level was dropping towards the last glacial maximum. But then as it really quickly rose up to present, sea level was rising so quickly that it didn't have time to erode this out. And there was actually, we caught into this thing with a hand core while we were diving. And it's an ancient lagoon still preserved in its place, which is really, really unusual. Also, the modern marine sediments were all laid down during this post-glacial marine transgression. And drawing in on one of the cores that I mentioned earlier, the one of the Choritz River, shown over here, with some of my German colleagues, we did a lot of analysis of evidence for past climates and for past sea surface temperatures and things like that. And we found two really interesting things in this core. We found evidence of the medieval climate anomaly, which is about 950 to 650 years ago. And that's, it was well documented in Europe, possibly the cause of the spread of the bubonic plague. It's a period of warming, and it hadn't really been documented in the Southern Hemisphere until now. We also found evidence of the Little Ice Age, which was analogous to the 1700s in the UK and in Europe, where people were ice skating on the Thames and everything was sort of frozen over. We also have evidence for that here. Our sea surface temperatures dropped too. And we find that pretty interesting, and we need to sort of consider that these events might be global phenomena. The sediment wedge, or the shelf sand, it's the same material that comes up and creeps onto the coast and forms our beaches and dunes now. It's all over the continental shelf. And the bottom image shows some pockets of these accumulated sediments in the lee of all of these coastal offsets along the Cape South coast. And that's because longshore drift and the dominant currents move from the southwest towards the northeast and push the sediments around into these embayments. In MOSSEL Bay, the sediments reach a maximum thickness of about 15 meters, which is pretty typical of the Cape South coast system. So taking all these geoscience things and looking at evidence for former landscape surfaces on this emergent shelf, some of the things that we can infer by linking geology to paleoscience more broadly are water resources. We showed through our work that there was evidence for a wet environment. So again, back to the Great Black River, back to the channel, and that lagoon that I told you about was over here. But there's another lagoon at a slightly deeper depth as well. And this lagoon has the same dimensions as Lungflay in Wilderness. It's about 2.5 kilometers long by about 0.5 kilometer wide. So there were significant available water resources on the continental shelf. Another thing that we've looked at is the possibility of stromatolites on the continental shelf. And stromatolites are fascinating things. It's the oldest form of life on Earth, and it's basically blue-green algae. But it appears in the Archean, which is way back in the early Earth, by about 3.5 billion years ago. For instance, around the rocks of Barberton, the Pongola supergroup, which is in KwaZulu-Natal, there are these stromatolite beds, which were the first evidence of life on Earth when the planet became an oxygen-based system. And interestingly, these stromatolites are still living now. They're living along the coast close to Cape Recife in Port Elizabeth. That's where they've been mapped out in quite a lot of detail. They've also been found in Morgan Bay in the Eastern Cape and in Shark Bay in Australia. And what we've been doing is considering that stromatolites are really good water resources at the moment. They're freshwater systems along a brackish coast. And they have very specific topographic structures. And I've been looking in our geophysical data and finding things that look like this, these pots or pits or pools or whatever, and they look a lot like stromatolite barrage pools. We haven't yet sort of confirmed that, but we have good reason to think that it's a possibility. And the reason that this is important is that the Cape South Coast rivers have very broad estuaries, and they're often salty up to a distance of about 17 kilometers inland. So if that was the case, and people were living on the shelf, they'd probably have a pretty poor chance of getting fresh water from the rivers and the estuaries that were at the present coastline. But if there were stromatolite systems for them to rely on, this would have been really significant. Looking at coastal change through time, in these 4 panels, I've just I've dropped sea level. And I was saying earlier that the Agulhas bank is really flat and really erodible. And the influence of the Cape Fold Belt sort of stops quite early on the inner shelf. So in Mossel Bay, at the moment, it's an embayed coast. And if you drop sea level to 30 meters, it's still an embayed coast. 40 is still the case. But by about 47 or 50 meters, the shelf topography means that the coastlines become increasingly linear. They don't have that same embayed morphology. And it means that you would expect broad sandy beaches when the sea levels are low, compared to rocky intertidal zones like we have now. And the same applies around the corner in Walker Bay. At Pinnacle Point, where the archaeological site is, there's a really great shellfish record. People have left behind their shellfish remains in the cave, and we've been able to take that really well dated, really high resolution record of shellfish and compare it to the geophysics from times of low sea level. And I've used one example here of 112,000 years ago, where people were exploiting things like Donax-Sera, which is a white sand mussel, Olycrical, which is turbo, and brown mussel, perno. And these two, Olycrical and brown mussel, are both hard intertidal zone, rocky intertidal zone shellfish. But the white sand mussel lives on exposed sandy beaches, not rocky coasts. So at 112,000 years ago, it seemed that there was, within a 5 to 10 kilometer radius, there was probably a sandy beach and some rocky intertidal zone areas. And when we zoomed in on the geology, dropped sea level to the time, to the depth where it was 112,000 years ago, and looked at this radius outwards from Pinnacle Point, we can see that the blue was probably outcrop of Table Mountain Group sandstone hard coasts, and the yellow was probably soft dissipative coasts. So we've started to test our hypotheses in both directions, which is really, it's quite exciting. And then I did this more broadly for the whole shelf and took the seismic profiles, those slices of cake through the seafloor, and I stripped off the modern sediment. You can remove these things using specialized programs, and was able to see what should have been exposed below there, and therefore what kind of beaches we expect at different times. So we've done that, and we've got a model of different beaches at different times, and we're starting to test it across different archaeological sites. Another thing that we've been working on is looking at raw material sources. So hunter-gatherers would have used a vast array of different types of geologies in order to make their stone tools. Quartzite cobbles were really popular for making hand axes and also flakes in the Middle Stone Age. Hornfels further north, but not really in this area at all. And silkreed, which has been specifically heat treated. So there's a lot of literature on the use of silkreed by hunter-gatherers and Middle Stone Age populations. And knowing where these outcrops are would have been really important to understand how people were sourcing their raw materials. So, for instance, cobble beaches like this would be great places for them to find materials to make tools. Hard grounds that are silkreeds or calcretes are also really good. And again, through seismic profiles, through these slices through the seabed, I was able to digitize different layers, and sometimes we would have samples of them or images of them, and we're able to see if it was cobble beds or hard grounds and how close these were to caves at different times. We have evidence for soils on the continental shelf, and of course soils would be expected on any landscape. Of course, these soils on the Paleo-Agulhas plain wouldn't have had that long to form, maybe 70,000 years in the time that sea level dropped and then returned. So although they're not sometimes as mature as some of the soil profiles that you expect on land, there is definitely evidence for things like hematite. And this is from one of the marine cores. Using the geology and our inference on soils, Richard Cowling, who's a good friend of mine, he's an excellent botanist and he specializes in fynbos. We put together soil distributions, and from that he actually modeled the possible vegetation on the Agulhas Plain. And this has been done before by John Compton in 2011, where he considered that there was probably a dominance of limestone fynbos, shale renosterfelt. So through our more recent work and through Richard's work on the soils and vegetation, we've been able to refine that a little bit. And what's pretty interesting is that finally, at last, this has helped answer a question that's had archaeologists perplexed for years. And that is that a lot of the archaeological sites on the Cape South Coast have faunal remains or bones from animals like this that graze on grassy plains. There's nowhere right now on the Cape South Coast that you would actually find these animals. I mean, it's massive quartzite mountains and a pretty narrow coastal platform. But now, understanding more about the substrates and the soils, possibly the vegetation, it's really, really likely that they were grazing out here, just adjacent to the present coast during times of low sea level. Further on the work with the vegetation, I wanted to also bring something in here which I think is super interesting. It's something that's had Richard Cowling puzzled for many years, was that the struntfelt, that element of fynbos, coastal struntfelt, it only occupies 1.2% of the Cape Floristic region today, but it's got a really, really diverse species range, and it's extremely biodiverse. It's packed with different species. And he's often wondered over his years of working on this why is it so sort of densely packed and so interesting when it occupies such a tiny area. But again, through the offshore work that we've done, we've seen that these dune systems, shown in yellow, expanded across this plain, and that the struntfelt would have been much, much more significantly exposed than it is now. So the struntfelt has mostly been submerged and destroyed, but there's only this little sliver left along the coastal plain now. But it was a much broader system. And we've compared it to the diversity in other Mediterranean climate ecosystems, like around the Mediterranean basin, in southwestern Australia, Chile, and California. And we see that our Paleo-Agulhas plain struntfelt is in fact much more diverse than those systems because of our very wide continental shelf out there offshore of the Cape Floristic region. I've got a good friend and colleague called Charles Helm, who studies ethnology or trace fossils, and he's done a lot of wonderful work on the coastal aeolianites all the way along the coast of the Cape South Coast area. He's worked from Arniston to Woody Cape, and in these cemented dune rocks, he's found trackways of a vast array of different animals and even humans. These are hominin track sites at Brenton-on-Sea. There were two people walking side by side across dunes, an adult and a child. These are about 90,000-year-old footprints, which is really spectacular. And they've got beautiful toes, which is why we know that they're definitely human. Other interesting species that he's found are giraffe near Still Bay, which was it was pretty strange to imagine giraffes in the Cape Floristic area. I mean, at the moment, giraffes are normally north of about 30 degrees south, and they prefer savanna landscapes, which we don't have here now. But along these very broad river systems on the Paleo-Agulhas plain, we expect a riparian vegetation, we expect savanna, floodplain types of environments. So it makes sense that there are giraffes in the area, in fact. He's found crocodile trackways, longhorned buffalo, which is now extinct. It was the Pelarovis capensis and had a horn span of about 2 meters. Cape giant horse, Equus capensis, it's also now extinct. Lots of these Pleistocene megafauna are extinct on many continents around the world. Australia is pretty famous for it. North America is pretty famous for it. And a lot of people believe it's because of the arrival of humans and hunting them. Elephants are pretty prolific along the Cape South Coast. Rhinoceros, Cape lion even. Pretty cool. That's also now extinct. So in order to test in more depth about where these animals were living. So we've got vegetation indicating that there were grasslands. We've got footprints and trackways of actual animals walking along coasts from areas above water now. We have bone records from the archaeological sites to show what people were hunting and eating. And we've also done a geochemical investigation of strontium, which is an isotope that remains in soils and plants. And when something eats or consumes the vegetation containing strontium, when that animal dies, the strontium is within the sort of tooth structures, within the tooth enamel, and you're able to study the proportions of that. And looking at the bioavailable strontium across the landscape, we went and sampled on all the different geologies and all the different soils and compared it to the values in the animal teeth from archaeological sites. We could in fact see that the values of strontium in the archaeological sites did not correspond to anything on the present landscape, and that the animals had to have been grazing in an area that's now offshore because it's the only thing we were not able to swim for. So lots of lines of evidence pointing towards the same thing. I'm going to start to wrap up and show you how I eventually made that map of the last glacial maximum. So it's not a modern day marine geology map. It's an ancient, it's a map of an ancient environment that's now 20,000 years old, and it's now submerged, and it'll never be exposed in exactly the same way again. So I took, of course, we always rely on existing data, and I took data from the 70s and the 80s by Dingle and his team, which shows the bathymetry and it shows the sediment distribution. I also took all of the mapping we did, seismic profiles, cores, dates, ages on rocks, ages on dunes, distribution of dunes. And it ended up getting too tricky using modern GIS systems. So I actually went back to older ways of doing things, and I turned on an old light table in the Council for Geoscience office. And I put everything on tracing paper and I drew it. It is accurate, it was all overlaid first. And I just started to add these layers and add this and add that. And eventually came up with the sketch of coordinates of this map of the PALAEO-AGULHAS plain. I then digitized it using AutoCAD and took it into GIS, and ultimately was able to make this map, which I showed you in the beginning. Of course, there are things that I'm going to realize were incorrect and we're going to change over time, but it's really exciting to have something to show for this work. Some of the significant features of it, I think I've zoomed in here, yes, is that the Gouritz River, I told you before that the floodplain was up to 18 kilometers across, but very, very shallowly incised rivers, no deeper than about 5-meter incisions. So the channel of the river would have been very shallow, very wide, very marshy floodplain, with riparian vegetation and savanna landscapes down the floodplains. And it actually splayed into a delta at the time of the last glacial maximum. And I saw this because we have a seismic profile that cuts across, and you saw multiple channels in this anastomosing sort of form. And there are no deltas on the Cape South coast at the moment. So that's really interesting for aquatic ecosystems and different vegetation and animals. Another thing that's interesting is the Alfred Banks. This is pretty famous to people who dive. It's offshore of Arniston, and it's an old volcano. It was the last puff or the last bit of activity when Gondwana finally broke apart. The South American Falkland Islands eventually pulled apart here about 58 million years ago, and there was a little volcanic eruption. It lines up with other similar volcanic plugs in Riversdale, Heidelberg, and Sutherland. But offshore, the Alfred Banks would have created very different soils, very different tools available to people. It would have been a topographic high on a largely flat landscape. The yellow bits are the dunes that are pretty widespread, and they would have been covered in coastal struntfelt vegetation, explaining again why the struntfelt is so diverse now, even though it's just a tiny little snippet of it at present. And the hard rock geology, which is shown in the same blues and greens from earlier, you'll see that it mostly terminates close to the inner shelf. And as soon as you get deeper than about 50 meters, the coastlines straighten out. The substrate is clay stones and siltstones, promoting things like grasslands, which looks totally different to what the environment looks like now. From the geology, we mapped out the soils, Richard Cowling and I, and we also see that we expect higher soil fertility during the glacial maxima, especially down these floodplains, especially on the dune environments and on the siltstones and the clay stones. Lots of renosterfelt, lots of different stuff. From the soil, we've inferred things about the fertility and the acidity and the depth.
This, of course, we want to continue testing, maybe with more offshore cores when we one day have the opportunity. But yeah, let's start at trying to understand and unravel this environment. So looking for a modern analog, there's only one place that we found so far, and this is the Agulhas Plain, which is between Bredasdorp and Cape Agulhas, where you drop down off the quartzite ridge onto that very flat marshy landscape, meandering rivers, lots of sort of marshy systems, little clumps of dunes with milkwood forests and things like that. This is basically what we expect much of the Paleo-Agulhas Plain might have looked like. Maggie Lambert-Newman, who's an artist who does a lot of scientific and geological art, she did this painting for us that shows these sort of straight coasts there, the mountains far in the background, plains landscape, plains animals, lagoons, estuaries, sort of marshy rivers, and she's also brought in some of the animals that have their bones in the archaeological sites, such as these grazing species, and here's evidence of the pillarovers, that giant Cape buffalo. So overall, the Paleo-Agulhas Plain is probably completely different to the modern coastal plain. The deposits on the emergent shelf show this expanded plain with shallowly incised, broad meandering rivers that float onto the shelf, wetlands, water table close to the surface. It's allowed us to reconstruct ancient habitats and compare to archaeological records. And we feel that it was a lot more fertile probably than the Cape Fold Belt foreland. Maybe helps us understand why people chose to live there and why people actually survived these fairly harsh glacials when they were living down there. So yeah, certainly ongoing stuff, and this is what we have so far. And yeah, that's all I got for you. Thanks very much.
Excellent, Hayley. Thank you very much. What a fantastic study, and the dedication that you've devoted to unearthing those secrets. I'm always impressed by the methodologies that the geologists use to discover the secrets of the Earth. One quick question, please. Can you make a comparison between what they found at the Pinnacle Cave and what can be found at the Kelders Cave here near Hermanus?
Yeah. So the De Kelders archaeological records they've been published, especially in the 90s and the early 2000s. And they actually have a lot of similarity to things at Pinnacle Point and at Blombos, where there are times when sea level was nearby and people were exploiting a system that was kind of similar to at present. So for instance, when the sea level was close, the mountains would have been close by, the rivers would have been similar to what they are now, the beaches and dunes. And then when sea level drops between the periods of warming towards the glacial periods, generally there's an increase of grazing species. There's evidence for different kinds of shellfish that were being exploited, such as Donax sera more than Perna. It's a very similar story all the way along the Cape South coast. It's that this was a coastal ecosystem and people were almost certainly shifting onto what's now the continental shelf when sea levels were low, and they were using those resources. And there are also times at all of these caves when people disappear completely. And it's probably when sea level was very low and they were not living in the caves that are now along the coast. People would have been living either in like a strandloper kind of environment out on the continental shelf, or maybe in other caves that are now submerged underwater. So in De Kelders, it's the same sort of broad pattern as at Pinnacle Point or the Classies River mouth, Blombos, where the archaeological records show very strange stuff compared to the modern environment when sea levels were low and when people were using the shelf.
Thank you. I want to ask you a second question, which is unfortunately not related directly to your talk. You mentioned the Cape Fold Belt a few times in your presentation. I want to make sure that all our listeners understand what that is about. If you have a map available, can you quickly run us through that?
So the Cape Fold Belts are the Cape Mountains that we all know so well. They're folded mountains so that they've got a folded structure, and they formed 250 million years ago or so when Gondwana was actually being accumulated. So Gondwana is a supercontinent that consisted of Africa, South America, Antarctica, Australia, Madagascar, and India. And when Gondwana assembled about 300 million to 250 million years ago, continents collided, they came together. And where you have two continents colliding, you have forced upward movement of the ocean between them and of those land masses themselves, which make fold mountains. So we have these Cape Fold Mountains here, which are much like the Himalayas when India collided with Asia, the same sort of system. The Atlas Mountains in North Africa, the Alps. And these are different to volcanic mountains that form either when you're pulling something apart or when you're pushing ocean floor against continental crust. And the Cape Fold Mountains around the Cape Mountains, as we all know them, they consist of rocks that are 550 million to about 370 million years in age that were already laid down. The collision happened about 250 million years ago to make the Fold Mountains. The rest of those mountains are in South America because as Gondwana was building up, the mountains were forming. And Gondwana existed for quite a while. And then eventually when it broke apart, fragments of these Fold Mountains ended up on different continents. And our Fold Mountains don't extend too far offshore for the most part because everything was pulled apart and the oceans opened.
Very good. Thank you, Hayley. That was a good, quick explanation. Actually, tectonic plate movements and continental formation is almost a lecture all on its own, but you did well. I have a question here from somebody. What was the length of the core samples that you drilled?
Oh, up to 6 meters. They were vibra cores. So we cored into ancient river channels and ancient lagoons, and normally the cores were 6 meters in length, and often we got the top part being the river or lagoon, maybe 3 or 4 meters, and then the sediment below that as well.
Okay, there's another question. Were there a lot of edible plants in the flora, or was the human diet mostly protein, like seafood and animals?
Yeah, there were also certainly edible plants in the fynbos. Unfortunately, those don't always preserve as well in the archaeological sites. So what do preserve from plants are phytoliths, which are little silica, they're sort of pockets in plants that get filled with silica. And these have unique structures and shapes, and they can be identified based on those structures. And those cannot be destroyed. I mean, they're tiny, they're microscopic. You need to study them under microscopes. But those phytoliths that are preserved from grasses and plants, those are preserved in the archaeological layers. It's very rare to have actual plant fragments remaining. The archaeological sites up the east coast, like Sibudu Cave in KwaZulu-Natal and Waterfall Bluff at Pondoland, where there's a totally different climate sort of system and things are a lot more humid and plants for some reason preserve better. There's evidence of actual bedding and plants leaves from things that would have been eaten or used medicinally. But in the Cape, it's mostly phytoliths that give an indication of what was there. At the moment, I've got a colleague and a friend who works at Nelson Mandela University. His name is Jan de Vink, and he's from Stilbaai. And his master's and his PhD work, and his subsequent work now, is based on ethnographic records. So he works with communities in the area that still rely on using fynbos for all sorts of those traditional purposes. And he's learned a lot from the people now in the modern ethnographic record. And he's compared that to pollen records from cores and phytoliths from sites. And he's seen that a lot of the uses of fynbos now are very similar to what they were right back into the Middle Stone Age, which is pretty incredible. So yeah, there is evidence of plant use.
Hayley, are you planning to map the Walker Bay area similar to what you did in Mossel Bay?
Oh, I would love to. So we, at the moment at the Council for Geoscience, I'm heading up an offshore mapping program. And that's the intention is to map like that across the whole exclusive economic zone, our whole offshore area. And it's something that it's going to take at least 10 years if we work with multiple vessels and multiple teams, but probably closer to 20 years. Unfortunately, our government mandate is based on poverty nodes, presidential poverty nodes, which means we've got to start work in areas that will have the biggest upliftment potential and that sort of impact. So we've started that program in the Eastern Cape. We're going to be working offshore of parts of Algarve Bay and the Wild Coast at first. But ultimately, I would love to get back to work in the Western Cape, and especially off Walker Bay. We've done quite a lot of work off Table Bay and False Bay because they were close to our office when we got this going, to sort of give an idea of what we can produce for the whole coastline. And now our operations have been taken slightly east. But yes, we will eventually map out there, and I really look forward to doing that. It's a fascinating seafloor.
Hayley, what I've noticed during the various geological lectures that we've had and looking at geological maps, the ocean floor along the western coast drops off very sharply. It does not have the kind of coastal plain that we see along the southern coastline. Is that because when Gondwana land separated, it sheared away the coastal plain?
Yes. So our whole continental shelf was shaped when Gondwana broke apart. So when Gondwana broke apart and the oceans opened about 140 million years ago, that's when everything either pulled apart gently and slowly or sheared apart, which meant that the Falklands microplate, actually it was like a strike slip fault. It sheared margin, and it made a very steep margin in some places. The skinniest part of our continental shelf is up the east coast, on the Wild Coast, and on the north coast. And that's only up to 8 kilometers in width. And in fact, I'm working on a project also up there that we've been doing for the last 10 years in Ponderland, the northern part of the Transkei, that looks at the same kind of thing, archaeology, geology, but looking at a skinny shelf compared to the wide one on the Cape South Coast. The west coast is somewhere in between the east and the south, I would say, in terms of width. So where the Cape South Coast is up to 200 kilometers of continental shelf, and the east coast is about 8 to 10 kilometers. The west coast is probably like 20 to 40 on average. So it's something in between. But the west coast is obviously of great interest to diamond miners. We don't have a lot of data from that area because it's all been locked up in proprietary work, and it's all very classified. So I know quite a lot about the area around Langebaan and Saldanha, where I've done some work, but further north than that, I don't really know much about the detail of the shelf, unfortunately. It's very secret.
Hayley, were you able to determine whether sea life at the periods that you were studying was very different from what we see today?
That's actually a fascinating question. That's something I've thought about because reefs obviously disappear or reappear. So when you're dropping sea level towards the glacial maxima, if you're dropping sea level 130 meters, most of the reefs will then no longer be reefs. They're going to be above water. So I expect that fish species and general sea life will adapt accordingly. Often when sea level is dropping, they have a lot more time to make those adaptations because it rises much faster than it falls. That's just a function of energy and melting compared to accumulating. But we know from the archaeological sites what people were fishing, hunting, collecting, picking up on coasts. There were whales because there's a whale barnacle at Pinnacle Point. So people were probably eating bits of washed up whale. There's some evidence for that, but it's really difficult to know for sure. And also a common problem, even with things like sharks, because they're cartilaginous, they don't leave skeletons, only their teeth. So like there's all these stories about those megalodon sharks, those giant Cenozoic sharks that went extinct millions of years ago. The only thing that remains of them is their teeth. There are no shark skeletons because you can't have those preserving. So it's really difficult. Actually, bony fish, you could find evidence for fish bones in archaeological sites. You sometimes find whale bones. cemented into rocks from the ancient records. But a lot of the marine life, it's really difficult to know what was there at different times.
Finally, Hayley, thank you once more for a really fascinating presentation. Thank you for your time and for the clear manner in which you explained all of this to most of us who are not geologists by training. Thank you, everybody, for attending, and all the best. I'm ending the lecture now. Goodbye.